So let's talk about our last of Newton's three laws. Newton's third law reads as follows. If body A exerts a force on body B, then body B exerts a force on body A. These two forces have the same magnitude but are opposite in directions. These forces act on different bodies. Okay, so that's all of the conceptual knowledge of Newton's third law in 3 sentences. Let's be clear about what we mean here. We're talking about two different objects, object A and object B. If object A applies a force to object B, then it means that object B must also apply a force to object A, and those two forces must have the same magnitude. Right? If one is 20 newtons, the other one is 20 newtons, but they're in opposite directions. Right? So therefore, in equation form, Newton's third law becomes the force of A on B is equal to minus the force of B on A. Right? They have the same magnitude, they only differ by a negative sign. They're in opposite directions. And again, we're talking about two different objects, and that is a key concept here, which we'll talk about in the next few slides. So one nice picture of Newton's third law is this one. We have a swimmer who's flipping around and pushing off the wall of the edge of the pool, and that person is applying a force to the pool, right? The force of the feet on the wall. Right? They're applying a force to the wall. So why do they end up flying off in the other direction? Well, there's an equal and opposite force, a force of the wall on your feet, which pushes in this direction, causing acceleration in this direction. Right? So in order for this person to accelerate in this direction, they apply a force in this direction to the wall, and the wall applies, by Newton's third law, a force in the opposite direction, which gives them that acceleration. Okay. Another nice example of this is just running. Every time you walk or run, you're using Newton's third law. Right, to start moving forward, you push backward on the ground with your foot, and then by Newton's third law, the ground then pushes forward on your foot, and your body as a whole then accelerates forwards. Right? And so it's the external force provided by the ground that is actually moving your body. Right? So this runner is pushing down on the ground at some angle, and the ground is pushing back on the runner. Right? With a force of exactly the same magnitude, these force vectors have the same lengths, but they're in opposite directions. Okay, so it's actually the ground which is pushing you forward as you run. So let's now try to really clarify our understanding by talking about what could be considered a paradox by some. Right? So if an object pulls back on you just as hard as you pull on it, how can it ever accelerate? Right? Is Newton's third law saying that nothing ever moves? That seems a little bit strange. So let's use this example of a donkey pulling a truck that is broken down. Right? So your truck is broken down, and this donkey is going to pull you back to your garage. Okay. If you want to understand how this donkey is going to cause an acceleration of the truck, if the truck is also pulling back on the donkey, we need to be careful about what forces are acting on each object and think about all the forces involved. All right, so let's draw free body diagrams. Let's draw diagrams containing all of the forces acting on each object. All right, so for the donkey, I have the weight of the donkey pointing down. I have the normal force, the force of the ground on the donkey, just the force of the ground that's stopping the donkey from falling through the ground upwards. I also have the force of the ground on the donkey, meaning the donkey is pushing backwards on the ground, so the ground is pushing forwards on the donkey, right? Just like that example of the runner running. Right? And then finally, we have this force backwards on the donkey because there's this tension in this rope, and there's this force of the truck on the donkey. Okay, now if I draw a free body diagram for the truck, I again have the weight of the truck and the normal force acting on the truck, and then in the forwards direction, I have the force of the donkey on the truck. So definitely on the truck, it looks like I have a net force, right? I have an unbalanced force here. This force is in the plus x direction. It's going to cause acceleration in the x direction. And I can also see that I have a Newton's third law pair here. The force of the donkey in the truck is equal and opposite to the force of the truck on the donkey. Right? So these two forces, which are equal in magnitude and opposite in direction, but they're acting on two different objects. Right? The force of the donkey on the truck, the force of the truck on the donkey. So what causes the donkey to move forward if they have this big force pulling back on them, the force of the truck on the donkey? Well, they have to be pulling forwards with a greater magnitude of a force. Right? So they're pushing on the ground with a large force, and the ground responds with Newton's third law of giving the force of ground on the donkey. So if this force is bigger than this force, I'll have unbalanced forces in x, and that donkey will accelerate forwards. Okay. So again, we need to highlight the Newton's third law pair here. It's always going to be on two different diagrams corresponding to two different objects. Okay, and so, but no matter what, these two vectors will have the same lengths, they'll have the same magnitude, and point in opposite direction. And so when you're solving problems where you have multiple objects, this equation may be necessary for you to solve the problem, right? That you can relate these two forces together. And we'll get some practice with that and some example problems coming up.